Hello all, welcome back. Today we will be continuing with the previous topic, that is from the liquid propellant rocket systems in the subject of aerospace propulsion. Right? Continuing with the previous topic, we will be starting with your propellant feed systems. Previously, what we have discussed regarding the propellant tanks as well as their arrangements, in what way they can be arranged in a complete rocket system. Now, what is a propellant feed system? Is basically the main functions for this is to raise the pressure of the propellants that are being fed into the combustion chamber for burning, as well as to supply them at the designed mass flow rates to one or the more required thrust chambers. Now, the energy for these functions either come from a high pressure gas or centrifugal pumps or any combination of these two. Now, the selection of the particular feed system and its components are governed primarily by the rocket application, duration, and the number or the type of thrust. And these are all based on the past experience and the type of mission, as well as by the general requirements and the simplicity of design, ease in manufacturing, low cost, as well as a minimal inert mass. Right? All the feed systems should and must consist a set of pipings, a series of valves, provisions for filling, and usually also for removing which contains draining as well as flushing of the liquid propellants, filters, control devices that are required to initiate, stop, and regulate the flow of the propellant and their operation. Now, this one is a figure represents the type of liquid propellant feed system that are available. A brief classification for the same, which we will discuss now. Now, propellant feed systems are classified under two categories. Particularly, first one will be under pressurized systems, or the turbopump systems. What is a pressurized system? In which you will be pressurizing the propellant system by adding a gas or by any external element. Whereas for turbopump system, you will be using turbines or pumps to pressurize the liquid propellant lines. Now, first we will discuss regarding the pressurized systems, where the first one will be your direct gas pressurization. Now, what is direct gas pressurization? You will be directly forwarding or putting up the air, particularly the gas, into the liquid propellant tanks to pressurize the fluid to push itself out. Other one would be flexible bag within the tank. A similar kind that we have discussed yesterday. What this means? Basically, you will be having a small thin layer of metal or a diaphragm which is pressurized by an external gas to push the liquid out. Other one will be your piston pressurization, similar to what we discussed earlier. Now, these three can be attained by having an inert gas or vaporizing a propellant. Right? The third one will be a chemically generated gas. A gas that we are having as a separate inert gas, which whatever we have, we can show it down, will be put it for regulated pressure mode or the blow down mode. Whereas the same gas, either the propellant or the inert gas, can be heated. Right? Heated to use among these two. Similarly, if you are shifting for turbopump systems, there are three major components that we are supposed to look after. First one will be a pump, turbine, as well as the gas power supply and gas discharge. Right? Now, pump, in order to maintain the required pressure or the desired pressure, we can have either single stage or multi-stage impellers, right, connected to your pump. Now, what happens for this? Small portion of one of the propellant flow is raised to a pre-combustion pressure with additional impeller. Whereas one pump there are separate pumps, one for fuel as well as one for oxidizer to maintain the pressure. Whereas two main pumps plus two booster pumps in order to get additional pressure as of your requirement. Now, coming for your turbine, what does the turbine do? Basically, either it can be a hot gas turbine or a turbine that is driven by the liquid propellant, particularly for boosting the existing pump, right? And a hot gas turbine, it can be classified under single stage or two stage, where one turbine is used to drive both the pumps, right? Or one or two separate turbines are used for one for oxidizer, one for fuel pump, or two main pumps, or sorry, two turbines which are main connected to your pumps, whereas other two which help you to increase the overall output. Now these are further classified under into a direct drive or with a gear transmission. Now coming to your gas power supply, we will be having under pre-combustion chamber, right, or a separate gas generator, a warm hydrogen from a cooling jacket, as well as a gas bleed from a main chamber. Now what happens under this? Under third classification under turbopump systems, you will be having a gas line, right? A gas line that is based on the pre-combustion chamber. That's before entering into the combustion chamber itself, you will be burning it, then using the same line to pressurize the propellant system, or use a separate gas generator that takes small amount of a small fractional amount of propellant, that is from fuel as well as the oxidizer, to burn separately and pressurize the system. Or other one will be to warm, let's say if you are using some hydrogen based liquid propellant, hydrogen which will be stored under cryogenic conditions will be heating up as the rocket moves, right? So that that hydrogen will be using for cooling, right? And the same gas can be reutilized in order to pressurize the propellant system or the propellant field line. Next one will be a hot gas bleed from the main combustion chamber. What happens during this? Upon combustion, a small line, right? A small line of the exhaust gases, particularly the combusted gases, will be taken into account for a complete tank, right? Upon combustion, the same thing will be taken back to pressurize the required propellant tanks. Now, all these, particularly separate gas generator, will be having further classification in terms of the flow through turbines either in series or in parallel, right? The flow or the gas that is being generated is used directly either to run two separate turbines, particularly for the fuel as well as the pump, either in series or in parallel. And based on that, what we can do, we can reuse, right? We can reuse the same gas after utilization and merge the same into my combustion chamber. That is where the area ratio of the nozzle is less, then we can send the exhaust on that direction, or into the diverging section, or to the main injector of the combustor. So based on all these, we can redirect the used gas onto my combustor, particularly the rocket engine. Now, in general, the gas pressure feed systems give superior performance compared to my turbopump systems when the vehicle's total impulse or the propellant mass is relatively low, the chamber pressure is relatively low, and the engine thrust to weight ratio is low, that is usually less than 0.6, and when it is repeated in short duration thrust pulses, here the usually heavy walled propellant tanks and pressurizing gas that constitute the major inert mass of the engine system. And in turbopump feed systems, propellant tank pressures are much lower, that is by a factor of 10 to 40, and thus vehicular tank masses are much lower by the same factor. But turbopump systems usually give superior performance compared to the gas feed systems, where the vehicle's total impulse is relatively large and the chamber pressure is high, which causes the mission velocity to be achieved higher. Now, coming to your local flows, in order to understand for gas as well as the turbo feed system, we'll understand the typical local flows and the pressure that are observed are and aligned in your any feed systems. Now, key parameters of any feed system description of in a liquid propellant rocket engines involve the flow magnitudes, particularly the oxidizer as well as the fuel flow, including the subsystems, thrust chambers, flow passages, together with the local pressures, that is, the pressurizing gas subsystems. If the flow diagram of a relatively simple rocket with a pressurized feed system shows that a gas flow is split between two branches and a propeller flow splits into pipes leading to each of the thrust chambers. The highest pressure resides in the high pressure gas supply tank, whereas the pressure drops along a line and pressurizing the gas subsystem, particularly the pipes, valves as well as regulator, and then drops further in the liquid propellant flow subsystems and more. As the liquid propellants flow into the thrust chamber where they burn in at the chamber pressure, the gas pressure always reaches a minimum at the nozzle exit. It is possible to predict a relevant drop in pressures as well as the flow distributions when enough information is known about all the components and their flow passages. If such analysis can be validated by the data of previous pertinent tests or prior proven rocket engine flights, it will have a high confidence factor. Most of the rocket engine design organizations have developed software for estimating pressures and flows at different parts of an engine. Knowing the local flows and local pressure is important for the reasons such as the information that we are getting out of the complete flow system is used for stress analysis and sometimes in thermal analysis also for the related components as well as the subsystems. They are needed for rocket engine calibrations that every engine will operate or is intended to operate, and the intended mixture ratio of fuel as well as the propellant, the chamber pressure, and as well as the thrust. And these tasks are accomplished by simple control devices or simple orifices that adjust the pressure based on the data that we provide. The measurement of actual flows as well as the key local pressures during the engine ground test or during operation and the subsequent comparison with the predicted values make it possible to identify discrepancies between practice as well as the theory, and such discrepancies can yield clues to possible malfunctions, inadequate designs and fabrications, all of which may be possibly corrected. If the actual values can be compared with analysis in real time, some experimental test hardware can be saved from the self-destruction. Sometimes analyses are done for strictly transient conditions, such as either for starting of a rocket or shutdown or during changes in thrust, that is particularly the throttling of a rocket. And transient analysis must also provide information for filling an empty propellant flow passages at different propellant temperatures for Warhammer as well as the valve reaction time, sloshing, everything. Now, coming to my gas pressure feed systems, which is one of the simplest and most common means of pressurizing the liquid propellant as well as forcing them out of their respective tanks by using a high pressure gas. The rocket engines with pressurized gas systems are reliable, but a rocket engine with gas pressure feed system was first to be tested and flown in the year of 1926, and there are two types of pressurized feed systems that are still often used today. The first one uses the gas pressure regulator in the gas feed line, with the engine operating at essentially constant tank pressure and nearly constant thrust. This is shown schematically in the figure that we will be discussing next, and which consists of a high pressure gas tank and a gas starting valve, a gas pressure regulator, propellant tanks, propellant valves as well as the feed lines. Additional components such as for filling, draining provisions, check valves, filter, flexible elastic bladders for separating the liquid from the pressurizing gas, as well as the pressure sensors or the gauges are also often used or incorporated during the time. Now, this gives you a small figure figure for any gas pressure, particularly gas regulated feed systems, where you will be having a high pressure gas supply tank at the center, right? An oxidizer tank, a fuel tank, your combustion rocket thrust and combustion chamber, with all the check valves, all the drain valves, everything. Now, first, when filing, particularly when filling, all the tanks are emptied out through my drain valve, right? Next, upon completely venting or completely emptying the tanks, from the filler neck, the propellant is fed in, right? The propellant is fed in to your tanks. Now, after certain proportion or certain volume of filling the propellants, what we'll be doing, we'll be closing these up, and this small cavity, right? After the small cavity, based on the small cavity, the fluid, particularly the propellant, either oxidizer or hydrogen, they tend to evaporate based on the ambient conditions, right? Now, these ambient conditions are to be maintained regularly, and in case based on the ambient conditions, as the fumes, particularly the propellant fumes, are pressurizing the whole tank, in order to maintain that, we'll be using a tank vent valve for maintaining the required pressure as well as emptying out the unwanted evaporated propellant gases. Now, whenever, in order to, let's say, an engine under operation, what happens is basically a gas supply tank, a high pressure gas supply tank will be having either inert gas or propellant at high volumes or high compressed rates. So first we'll discuss only for inert gas, we'll understand. Now, what happens on the inert gas? A gauge is maintained to check whether a required pressure is being maintained in the high pressure one or not. Next, bleed valve is maintained to remove any excess amount of gas that is being happened or stored under the gas supply tank, and a fill valve is used for filling the high pressure gas. Now, when under operation, the pressure regulator maintains the required pressure, right? As the propellant level decreases, particularly in the both tanks, fuel as well as the oxidizer, the pressure regulator checks or maintains the pressure that is required to have the fluid at the level, right? For example, better example, as there is a drop and before operation, the pressure regulator will try to maintain the pressure in the fuel tank as well as the oxidizer tank at some certain level, preset level. Now, after certain work or after certain period, what happens? Basically, as the rocket works on, the propellant is being taken through the filters, then onto my propellant valves, then to the orifice in order to control the flow, then to the rocket thrust chamber. Additional, based on the number of thrust chambers we require, multiple additional components of the same can be added up. Now, as it operates, the volume of the propellants will decrease. Now, as the volume decreases, there is some sort of vacuum that is being formed. So, in order to restrict the formation of vacuum, the pressure regulator maintains the pressure at the rate at which the propellant is being consumed, right? So, proportional form, right? So, on the same basis, the gas pressure fed systems will be working. Proportional to the pressure that is to be maintained, a constant pressure is being maintained for constant operation. Now, after the tanks are filled, the high pressure gas valve is in the figure, that is remotely gets actuated and admits the gas through the pressure regulator at a constant pressure to the propellant tanks. Check valves prevent mixing of the oxidizer with the fuel, particularly when the unit is not in an upright position. The propellant are fed to the thrust chamber by opening the appropriate valves. When the propellants are completely consumed, the pressurizing gas can also be used to scavenge and clean lines as much of the liquid propellant residue. Any variation in the system, such a combination of several valves into one or the elimination of additional certain components, depend on the type of application and the type of rocket that we have designed to use. And if a unit is to be used and flown repeatedly, such as a space maneuver rocket, it may include several additional features such as thrust regulating device and a tank level gauge. These will not be found in any expendable single shot units, which may not even have a tank drainage provision. A second common type is my gas pressure feed system, and which is also called as my blow down feed system, which we will be discussing in the figure that is being shown on the next slide. Here, the propellant tanks are larger because they store not only the propellants but also the pressurizing gas at an initial maximum propellant tank pressure. There is no separate high pressure gas tank or no pressure regulator. The expansion of the gas is already in the tanks provided for the expulsion of propellants. Blowdown systems can be lighter than a regulated pressurized system, but the gas temperature, pressures as well as the resulting thrust all steadily decrease as propellants are consumed. Now the figure shows the blowdown system where the pressurized gas is stored inside the propellant tanks. Now, where gauges are available to determine the pressure that is being fed, that is inside the tank, and vent, gas fill as well as the drain are available on the two ends of the tanks, propellant tanks. Two propellant tanks consisting of the fuel as well as the oxidizer, and these are connected to my fill as well as drain valve, then to the filter, then on to the combustion chamber. Now what happens under this? The gas, particularly the inert gas or the gas of the propellant itself, is being maintained inside the propellant tank. So what is the comparison? Simple. Particularly the pressure or the thrust, it basically is a constant, right? A constant pressure or constant thrust is being generated under regulated pressure, whereas in a blowdown the pressure decreases as the propellant is consumed, because initially the gas that is being stored under high pressure, right, as the volume decreases, gas expands, decreasing the pressure of the gas, right? Now coming for a gas storage, for under regulated pressure mode, we'll be having or we'll be storing it under separate gas tanks, whereas under blowdown the gas is stored inside the propellant at initial tank pressure with a large ullage that is up 30 to 60% of the cavity. And what are the main required components for regulated pressure mode? We need a regulator, filter, gas valves as well as a gas tank for the gas that is to be stored, whereas for a blowdown type we need a larger and heavier propellant tanks because it's supposed to maintain the pressure of the gas that is already pre-fed, as well as we are supposed to maintain we are keeping the propellant as well as the oxidizer within the same tank. Now what are the advantages for using the regulated pressure one? Is merely you will be getting a constant pressure feed that gives essentially a constant propellant flow, which in turn gives you the constant thrust as well as the force. Now for blowdown one, it is a simpler system as well as there is less gas required and the inert mass of the rocket vehicle can be minimized. Next, what is the advantage? You can better control the mixture ratio of your propellant as well as the fuel by controlling the pressure individually for both the propellant tanks, that is oxidizer as well as fuel, and maintain the individual mixing ratio as of your request. But in case of your blow down type, there is no high pressure gas tank. Whatever the gas that is being maintained in the tank will expand gradually till the complete consumption of the propellant inside the tank, but over a period of time the pressure decreases. Now coming to the disadvantages, what are the disadvantages that you can occur under regulated pressure mode is it is more slightly complex, right? The regulator introduces a small pressure drop as well as the gas that is being stored under high pressure often for a long time, particularly during storage or during stowage, everything, and which requires more of the pressurizing gas. Whereas for blow down type, the thrust decreases with the burn duration and somewhat higher residual propellants due to less accurate mixture ratio control. The pressure inside both the tanks will be maintained constantly and equally. That restricts our control of the mixture ratio. Whereas the thrust must operate and be stable over a wide range of thrust values and modest range of mixture ratios. The propellants stored under pressure are slightly having lower specific impulse towards the end of the burning time. Now coming to the tank pressurization, in what way you can pressurize the tank? What we have discussed till now is basically the gas pressure feed system. The objective of the feed system that we have discussed earlier is to move the propellants from propellant tanks to the thrust chambers. But the tank pressurization system is a part of the feed system that provides the propellant expellant gas. There are two types where first one, which includes the pressurized gas feed system that we have discussed earlier, where a relatively high pressure gas displaces the propellant from the tanks, and second one will be the pumper feed system where the main energy of the feeding the propellants come from either one or the more pumps. It requires the lower gas pressures and in tanks to move the propellants to the pump inlet, and it helps to avoid pump cavitation. There are several sources of pressurizing gas used in tank pressurization system. High pressure inert gases stored at ambient temperature are the most common ones. Heated high pressure inert gases that are typically to 200 to 800 Fahrenheit or 93 to 427 degrees centigrade reduce the amount of required gas and thus the inert mass of the complete pressurizing system. Gases created by chemical reaction either by use of liquid bipropellants, particularly hypogolic propellants, or the monopropellants, or alternatively a solid propellant, all at the mixture ratios or the composition which results in the warm gas. What do I mean by warm gas? Basically any gas that is heated from its initial position. Whereas coming for your hot chamber gases, hot gases, those are the gases that are after combustion temperature around 2 to 3000 degrees centigrade. Right? Now, next one will be an evaporated flow of a small portion of a cryogenic propellant, which is usually a liquid hydrogen or liquid oxygen, and by applying heat to the thrust chamber or cooling jacket or the turbine exhaust gases with heat exchanger, then using a small part of the same gases, particularly the cryogenic gases, and is again fed back to my tank to pressurize the same. A direct injection of a small stream of hypogolic fuel to the main oxidizer tank and a small flow of hypogolic oxidizer into the fuel tank has been tried by several countries, but due to the limited success, it is really another form of chemical gas generation. Next one will be my self-pressurization of cryogenic propellants by evaporation, which is feasible but is difficult to control. So the experience within that regime is limited. And in order to analyze or design or analyze any pressurizing system, it is necessary to have relevant information about the tank as well as the engine. This include basic engine parameters such as the propellant flow, the thrust that the rocket is being generated, the duration till which the engine has to work, and the pulse width, particularly the short durations during which the rocket has to work, the propellant tank volume, the percentage of ullage in the tank volume during storage as well as during operation. Next, the storage temperature as well as the range through which the propellant has to vary, propellant and pressurizing gas properties, are they soluble or not, everything. Next, the propellant tank pressures, gas tank pressure, and the amount of unavailable residual propellant, right? Many of these type items, a nominal value, maximum as well as the minimum value may be needed in order to identify the correct pressurization system as well as the feed system necessary for any liquid propellant rocket system, right? On the next class, we will be discussing regarding the factors related to your tank pressurization system as well as the cycles that any rocket, particularly the liquid propellant rocket engine system, follows. What are the gas cycles, what are the energy cycles, what are the flow cycles that any rocket system follows. With that, we'll close it for now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.